Hi, everyone. Welcome to the algorithm seminar. Today, we are very happy to have Andrés here to give a talk. He is currently a postdoctoral researcher at the Center for Mathematical Modeling at Universidad de Chile. And in 2024, will join EPFL as an assistant professor. He received his PhD from Universidad de Chile and was advised by Jose Correa and Paul Duting. His research is focused on the interplay between optimization and incentives. This is situations where the outcome depends on the actions of strategic agents. He's particularly interested in allocation problems with a dynamic aspect where decisions are made on the fly. He also often considers data-driven approaches in which decisions are directly made using observations rather than standard distributional assumptions. Modern platforms like routing apps, online advertisers, and online marketplaces face these challenges on a daily basis, and his work is centered on understanding the fundamental aspect that drive decision-making on these settings. Please welcome our speaker.
Thank you. Thank you for the introduction. This is a joint work with one of my former advisors, Jose Correa, and the title is "A Constant Factor Profit Inequality for Online Combinatorial Auctions." Now, what is an online combinatorial auction? In this problem, we have a set M with M items, and we want to allocate these items to a sequence of n agents that arrive one by one. These agents have preferences for the items expressed as valuation functions that are drawn independently from certain distributions f1 to fn that are supported in a given set V, which is a set of monotone and subadditive valuation functions. Now, these valuation functions, as the name suggests, are functions, are not just a number for each agent. For each agent, we have an entire function, and these functions map subsets of the items into a value. So the number vi of A, where I is an agent and A is a subset of the items, is how much agent I is willing to pay for the set A. So for each agent and each subset, we have one such value. And as I said, these functions are drawn independently from certain known distributions f1 to fn. Now, we want to do this allocation of items to agents online. So first, we receive the valuation V1 drawn from F1, and we want to decide right away which items go to agent 1. Next, we receive valuation V2 drawn from F2, and we want to decide which of the remaining items go to agent 2, and so on and so forth. And our objective is to maximize the expected social welfare, which is the expectation over the randomness of the evaluation functions of the sum of how much each agent is willing to pay for the set each of them receives. Now we want to do this maximization online, and we want to compare whatever we get against the expectation of the optimal partition we could do offline. That is, if we could see all valuations in advance, there would be an optimal way of partitioning the set of items that maximizes the sum. So we want to compare the expectation we get online against this expectation. And this is also called the the value of the profit, and that's why this was called the profit inequality, because we compare against a benchmark that is what a profit that sees the future could get because he knows the future. So I said before that the distributions were supported in a set of subadditive valuations, but I didn't say what subadditive means. And subadditive means this constraint here. I require that for all valuation functions, this inequality is satisfied where if I take two subsets of the items, the valuation of the union of the two subsets is at most the sum of the valuations. These also are known as complement-free valuations because this constraint rules out a certain form of complementarity between the items. And it's a very large class and includes other classes of valuation functions that have been studied in the computer science and in computer science, but also in economics. We have the additive valuations, gross substitutes, submodular, XOS, which is also known as fractionally subadditive, and all these classes are subclasses of the subadditive valuations. No, we restrict the space of valuation functions because if we don't do this, then the problem becomes too difficult, and in fact, no good approximation is possible. Now, I want to mention some prior results that are interesting or related to what we do. First, if we consider the offline setting, so in an offline setting, we observe all valuation functions, and we have to output an allocation, a partition of the items, and which items go to which agents. We can do this in polynomial time and guarantee a two approximation with respect to the best allocation. We can also ask the question, what happens if these valuation functions are not public information, but instead private information of each of the agents? So that means we don't observe the valuation functions, but instead have to interact with agents that want to maximize their own utility. And there is this super nice result that says that the following mechanism achieves a two approximation. Run a first price auction for each of the agents, for each of the items in parallel, and then output that allocation. This in equilibrium results in a two approximation with respect to the best possible allocation. Now back to our online setting. If we restrict the valuations to be XOS, which is a strict subset of the subadditive valuations, we can guarantee a factor 2 profit inequality. And for the general case of subadditive valuations, prior to our work, the best result was order log number of items profit inequality. Now, if you look at this picture, you will see that we have a 2, and a log number of items, right? So why is not the last one also a 2? And there was an important open question whether it was possible to do a constant factor profit inequality for the online case when valuations are subadditive, and we answered this question. We showed that there is a constant factor profit inequality for this case, and interestingly, we developed techniques that are quite different from what was done for the two approximation for XOS and for the order log number of items for subadditive. And if we look into those results, there are two problems if we wanted to use those techniques. If we wanted to extend the result from XOS to subadditive, the first problem is that XOS valuations cannot approximate well subadditive valuations. In fact, there are subadditive valuations that cannot be approximated better than a factor log number of items. With XOS, and so that's a problem if you want to extend the result for XOS. And then for the log m result, in fact, the authors of that paper also show that their analysis is tight. So the same approach cannot be improved to a constant factor. So the techniques we do are very different. In those other results, they use something called balance prices. For those that are familiar with the profit inequality literature, we do something different, which is essentially based in two main ideas. One comes from sample-based profit inequalities. This is profit inequalities where we don't have access to the distribution themselves, but only to samples from those distributions. And the other main idea is a fixed point argument that in a way comes from the result that I told you before for the offline case when values are private information, where we can do this simultaneous first price auctions. So it's a combination of ideas from these two words. Please interrupt me in any point. I mean, if the setting was not clear or yeah, please, Bobby.
On this slide where you say the fixed point argument comes from first price auctions, I could picture two interpretations. One is that the analysis of the first price auction in that 2013 paper makes use of a fixed point argument. And the other is that merely asserting that there exists a Bayes-Nash equilibrium for the first price auction is implicitly using a fixed point argument, and that's the only usage. Which of those interpretations or are both correct?
So we use the fact that the equilibrium exists, and that's a fixed point argument. Yeah. But also we need part of the argument that shows that the first price auctions give a two approximation to argue that the fixed point is good for us as well. So I mean, so we don't use directly that result, but the modified version. But I'll give you more details in later slides. So first, this idea from sample-based profit inequalities is essentially this very basic observation about IAD random variables. If I have two IAD random variables, let's say they are absolutely continuous, what's the probability that one of them is larger than the other?
Half.
1/2, right? So if I have a battle between two IAD copies of myself, the probability that the red copy wins is 1/2. The probability that the blue copy wins is 1/2. And this is the essential observation we use. So how do we use this observation? As follows. So so as I said, in a sample-based profit inequalities, in a sample-based profit inequality, is like allocating one item to a sequence of n agents. And instead of having access to the n distributions, as in the setting I introduced at the beginning, we just have access to one sample for each distribution. So what can we do in this case? There is this very simple algorithm that gives a factor 2 profit inequality for the case of one item. We take each of these samples, let's call them B1 prime to Bn prime, and we define a threshold T prime to be the maximum of these samples B1 prime to Bn prime. All right. And there the algorithm is give the item to the first agent whose valuation is larger than T prime. Now, what's nice about this algorithm is that the maximum valuation of the real values has the same distribution as the threshold, right? Which means that with probability 1/2, we never sell the item or we never allocate the item, right? Because the maximum valuation will be below the threshold T prime, right? With probability 1/2. So nobody has a valuation that is above the threshold, right? And that means that if we have a particular agent whose valuation is larger than the threshold, then the item will be available when this person arrives with probability 1/2, right? Now, I can give you a very simple proof that this is a 6 approximation. As I said, it gives a 2 approximation, this algorithm, but this is a short proof that it gives a 6 approximation. So yeah, the expectation of the algorithm, we can rewrite it by linearity of expectation as this sum over agents of the expectation of the value of the agent times the indicator function that the agent gets the item, right? That's the expected welfare. Now, the indicator that agent I gets the item, because of how I define the algorithm with this threshold, is equivalent to 1, that the agent has a value that is above the threshold, and 2, that the item is available when the agent arrives, right? These are the two conditions that are equivalent to agent I getting the item. Now, T prime was the threshold, and let me introduce another sample of the threshold, an IAD copy of this maximum. When I said that the item was available for I, right? What does that mean? The item being available means that no one before agent I took the item, right? That means that none of the values of the agents that came before I had a value above T prime. Now, the maximum of the values of the agents that came before I are at most the maximum of independent realizations of all agents, right? So I can upper bound the maximum of valuations of previous agents by T double prime. So I can rewrite these two indicators as the indicator that Vi is larger than the threshold, and that the threshold is larger than an independent copy of the threshold, right? And then we can lower bound the sum over I of bi with the maximum over I of bi, which is just another copy of the threshold, right? So we get expectation of t, indicator of t larger than t prime, larger than t double prime. And now t, t prime, and t double prime are all IID values, right? T, t prime, and t double prime. So, and now there, if I have three IID values, right? There are 6 possible orders of these three IID values. So we get 1/6 times the expectation of one of them, at least. So that's a simple proof of this 6 approximation. Now, we would like to do a similar analysis for our case with M items. So we would like to do this in parallel for each item. The problem, if we wanted to do this, is that we don't have a number per item, right? If we had additive valuations, then we could do this because additive valuations would give a number per item for each agent. But we have these subadditive valuations that give a value per subset and not per item. So the question is, can we translate subadditive valuation functions into item values? And the answer is no and yes. No, because additive valuations cannot approximate well subadditive valuations. Not even fractionally subadditive valuations can approximate well subadditive valuations. But yes, because of the following. Remember, I told you there was this 2 approximation using first price auctions. So let's look more carefully into this result. It says, if we run simultaneously for each item a sealed bid first price auction, then we get in equilibrium in expectation a 2 approximation. Now, what's this mechanism? I said we will run simultaneously for each item a first price auction. That means that a given agent I has to submit a bid for each of the items, right? I have this, in this example, I have 3 items. So agent I has to submit a bid for the strawberry, one for the avocado, and one for the blueberry, right? And also each all other agents have to do the same, right? So we get n bids for each item, and then we give each item to the highest bidder, right? That's the mechanism. If there are questions, again, please interrupt me. Now, what is an equilibrium in this game? This mechanism now defines a game for the agents, right? So what is an equilibrium in this game? An equilibrium, right, is a set of strategies for each agent that maximizes their expected utility, right? Now, what is a strategy now? A strategy is a mapping from valuation to bids, right? So in equilibrium, the agent has a mapping from the value to a vector of bids. I'm an agent playing this game. I observe my valuation. It's a complicated thing, right? It's a value for each subset. But to play this game, I have to submit a number for each item. So then the equilibrium of this game gives us a translation from values to bits to numbers per items. And this is what we use in our algorithm. So
Some questions.
yeah, sure.
You're approximating welfare.
Yes, social.
They show that there exists a pure equilibrium.
No, they don't show this. This is a good question. They don't show there is a pure Nash equilibrium. There is mixed Nash equilibrium. So this mapping is actually not deterministic. Is for a valuation function, it gives a distribution over vectors of bits. But this still it's something that transforms the valuation into pair item numbers. It's just there is some extra randomness on top of the randomness of the evaluation. So we define this object, the random score generators, which intuitively is just an equilibrium in some game, right? It's a mapping that takes valuation function and outputs a distribution over vectors of bits, right? The equilibrium is one such mapping, right? It's a bit like a black box because it's not explicit, but it exists. And then what we do is to take these little mappings, and we do what I said before. We will do this the algorithm for the one item now in parallel for every item. So in other words, what we do is we sample each of the evaluation functions. So we get v1 prime to vn prime. We map or we sample actually from the corresponding distribution of bits to get these bit primes. And for each item, we set as threshold the maximum bit prime for that item. Yes?
Just to make sure I understand the meaning of the word algorithm on this slide.
Yeah.
This is like an algorithm template parameterized by random score generator.
Yes. Yeah, exactly. Given these mappings DI, these random score generators, we have this algorithm. And this algorithm is we sample v1 prime to vn prime, we transform this into bits prime, we set thresholds t prime, which are the maximum bit for each of the items. And then when we get the true valuations, we again transform the valuation into bits using these random score generators, DI, and give the agent all available items for which the bit is larger than the threshold t prime. Right? So in this image, we'll give agent I all items j for which the bit of I for item j is larger than the threshold tj prime. And if you think of this for the single item is basically the same algorithm if this mapping is the identity, right? Now the key observation is similar to what I said before, these IAD realizations. If you think of the maximum threshold, sorry, if you think of the thresholds and the maximum true bit for each item, these are two IAD vectors, right? Not the entries of the vector IAD, but the two vectors are IAD between the two, right? And notice that I'm saying that I will allocate an item if someone has a bit that is larger than the threshold. So the set of items that are allocated at any point in the algorithm has the same distribution as the set of items that are never allocated, right? For which the threshold is larger than the true values. right? So essentially, the set of available items and the unavailable items has the same distribution.
Technically, I think you mean the set of available items is a subset of the J satisfying the first.
Yeah. Well,
A superset of the J satisfying the first inequality. Set of unavailable items is a subset of the one satisfying the second inequality.
so yeah, there is this caveat with the strict inequality, or what do you mean?
Going back to the argument for single item
Uh-huh.
that you gave, a key step in that argument was that for an item to be available, it needs to TJ prime greater than or equal to TJ double prime is a sufficient condition for it to be available. It's not necessary. In reality, it just needs to have not been taken by
Yeah.
numbered before me who's
Okay, yeah. I was trying to say this at the end of the. So at the end of the execution of the algorithm, this is exactly true, right?
like when at time n,
Yeah,
the final bidder comes in.
or even after the final bidder.
Yeah.
The set of allocated items is the same as the set of unallocated items. Not the same, but that's the same distribution.
Got it.
Okay, but then we can go specifically to what this implies. So, this key observation we synthesize it in something we call the mirror lemma, and this mirror lemma says the following. So, take the expected value agent I gets. Right, I can rewrite it as this. The value for the set of items J, for which the bid of agent I for item J is larger than the threshold Tj prime, and the item was available, right? Which is the threshold Tj prime is larger than the maximum of the bids of agents that came before, right? I claim that the expectation of that set is at least 1/2 times the expectation of the value of this other set. Si defined as I'll sample 2 copies of the thresholds, right? Two independent copies of the thresholds. Remember, the thresholds were the maximum bid of one realization of the bids, right? So I take 2 independent realization of the bids, and I define the thresholds at the maximum bid for each item. So I have 2 copies, the red one and the blue one. Here in the screen it's like orange, but I don't know how the rest is. Should be red and blue. So I have a red copy of the thresholds and a blue copy of the thresholds, and I define the set Si as a set of items for which the bid is larger than both copies. Remember that in the algorithm, my condition is being larger than 1 copy, right? But now I said, now the problem is that we have this online thing, so we need that items are available. Now I will say that I can forget about the online, the sequential part, by adding this extra copy of the threshold. And why is that? So fix the bit corresponding to the true values. These are the green ones. And sample these 2 independent copies, the red one and the blue. I can couple this with the execution of the algorithm in 2 ways. In one, the red one is the actual threshold, and the blue one is an upper bound on the maximum bid of previous agents. And And in the other realization, I do the opposite. The blue one is the threshold, and the red one is an upper bound on the maximum value of previous agents. Now notice that in these two realizations, I get the two parts of the green set, right? In one realization, the red set is available when agent I arrives. So we get one side of the green set. And in the other realization, the blue set is available when I arrives. So the other side of the green set is what I gets. And then we take these two realizations, which have the same probability, and couple all such realizations. And then by the subadditivity, the agent gets at least half times the value of the union of the two sets. We can actually do the calculations. Now, here I have the two versions where T is the threshold and where T double prime is the maximum of prior bits, and the opposite. Both are the same because they're IAD. So if I exchange them in the expectation, I get the same number, right? So I can just take 1/2 times the sum of both because they are the same number. But then I put together the two expectations, and I get, because of the subadditivity, I get at least the union of the two because I have the sum, and the subadditivity says that the sum is at least the union.
Is that the only place you use subadditivity in the whole proof, or is
No, there is
later?
we use it again.
Okay.
This is the first time we use it. So this is the proof of the mirror lemma. So we get at least half of this set, and as I said, this set is no longer defined sequentially, right? It only depends on these realizations and not on the order in which they arrive and what is available and what is not. So the good thing about this mirror lemma is that we can now think of this as a simultaneous allocation. And then, since it's a simultaneous thing, we can think of the version where the allocation was offline, but valuations were private information. Basically, what we can show is that these random score generators or random score generators exist, that random score generators that guarantee a good approximation exist. And intuitively, what we do is to design a synthetic auction similar to the first price auction, and we take the equilibrium of this synthetic auction. And we have time, so I think I can show you what exactly this is. So we want this mapping from values to bits that guarantees that the set S, which is what's written there, has good enough value, right? So then that means that we want the bits to be large compared to the thresholds T. But the thresholds T are defined with the same mappings, right? So if the bits are large, that means that also the T's are large. So what we do is to subtract
Universal quantifier over VI and
no, there's no universal. No, that's exactly the. It's for every distribution F1 to Fn, distributions F1 to Fn. This is true.
let me try rewording my question.
Ah,
The left side of the inequality is a conditional expectation.
yes.
So I am interpreting it
to be.
Oh, there is
Scalar
almost
quantity,
surely.
but a function of VI.
This is almost surely.
The
yeah.
right side is a function of VI as well. Okay, good. So the inequality holds almost surely
Yes.
over the sample space the VI is sampled from.
Yes. Yeah.
Great. Okay.
So, let's look at this inequality. So on the left or top, we have the set Si, right? This is how we define it, and we are subtracting the bits over the entire set. And this is essentially to compensate things to guarantee the existence. Because now I want the set to have high value, so this pushes the bits higher, but I want to push them to be lower, so that's why we subtract these bits. But intuitively, it's like I'm making agents to pay for their bits, right? And this would be their utilities. The value they get minus their bits. This is the utility.
It's not really a first price auction, it's more like an all-pay auction. Everyone's.
Yeah, if you look at this, it's more like an all-pay action.
Uh-huh.
Yes. So yeah, that's what I was saying. We designed like an auxiliary auction. And then why is this inequality true? I mean, or why are there RSGs that satisfy this inequality? Basically, notice that the right-hand side or the bottom side of the inequality only depends on BI. I mean, in the randomness sense, only depends on BI, not on the other valuations. So the set that maximizes the right-hand side only depends on BI, right? Given BI, we can compute, and assuming all the distributions are fixed, right? As in when we're analyzing an equilibrium, right? So we can compute this set X, and restricted to the set X, we can sample a third copy of the traces, T triple prime, right? And then T prime, T double prime, and T triple prime are all identically distributed. And that means that if we restrict to X, the set of X for which T triple prime is larger than the other two, right, is essentially 1/3 of the entire set. And here is where we use again the subadditivity, right? Because we couple all the realizations where the green, the red, and the blue are exchanged. So we get 1/3 times the value of the union of the entire set X, right? So that means that we can always find bits for which we get 1/3 of this set X. And then we pay in expectation one copy of the tracer, right? Because I said I will sample the bit as one copy of the tracer. And then it turns out one can write this as a mapping from the space of random score generators into itself. It's actually a set valued mapping. So by Kakitani's fixed point theorem, this has a solution. This inequality has a solution in the space of random score generators. The argument I told you before is the non-emptiness of this mapping. But it's convex and compact and everything. So by Kakutani's fixed point theorem, this has a solution. So the random score generators exist. And once we have this inequality, we plug it in the previous analysis, and it's just some manipulation that having these payments cancel each other with the term in this utility sort of term, and we get the sixth approximation. And that's basically the proof. I mean, the first step here is the mirror lemma, and then the other one is the lemma I just showed you. Yeah. So yeah, to summarize, we found this this new sixth approximation, right? We can implement it in an incentive compatible way, and actually we can do an explicit algorithm. All this thing was implicit because it required this black box thing, these things that we guarantee to exist but are not given explicitly. We can actually do an exponential computation to do it explicitly. And an obvious question is, can we do a constant factor in polynomial time? Right. All this is to guarantee the existence of an algorithm that we can compute in exponential time. Can we do a constant factor in polynomial time?
So, when you say exponential time, how are the valuation distributions specified in the input? Do you assume that they have finite support and the input just lists?
I mean, I'm allowing for exponential time, so so even if I mean exponential in n and m having value queries is enough to get exponential time, right?
Oh, so you only need a value query oracle for the.
I mean, for exponential time, yes, but I mean, of course, for polynomial time, we would require something different, right? Or maybe not. I don't know, but probably. I mean, if it's possible to do in polynomial time, I would imagine we would need to use maybe demand oracles. But yeah, I mean, when I say exponential time, it's basically observing everything. Now, a good thing is that to get a constant factor in polynomial time is enough to get a constant factor against the online optimum. Which I don't know if it's easier, but if it's easier, then that would be enough, right? If we have a constant approximation with respect to the online optimum, this would give a constant approximation with respect to the offline optimum as well. Another direction that is also open, and I'd say it's immediate from what I said, is whether a constant is possible if we do pricing, if we do posted prices. The two approximation for XOS and the log M approximation for subadditive are both using posted prices. That means we compute a price for each item beforehand, post these prices, and let agents take whatever maximizes their utilities. And this is a much simpler kind of mechanism.
Are you adaptive, or did you set the prices once and
They set the prices once. Yeah, this both of those results set the prices once. They're really posted prices. So the question is, can we do a constant factor for subadditive with posted prices? We don't know that. And yeah, that's it. Thank you. Yeah, I don't know if there are more questions. Yeah, well,
Near the beginning of the talk, you said we need to assume some structure on the valuations because otherwise you can't get good bounds for profit inequalities.
Yeah. Yeah.
And I know that you can't get like a constant factor or profit inequality unless you make some assumption
Yeah.
on the structure of the valuation functions. But is it possible that you could get like log number of items or polylog?
No. I think okay, there is a construction you're familiar with. The same for the intersection of matrix.
Yes.
That one I think gives a lower bound of log number of items if valuations are not subadditive. You can construct.
Yeah.
But there is a very recent result that I think is not even published, but I attended a talk like a month ago. And they showed that it's not possible to get better than O of m divided log m.
Wow. Okay.
This is very recent. It's by Jose Soto, Victor Verdugo, and a student of Jose Soto. So if valuations are arbitrary, monotone, it's not possible to get better than O of m divided by log m.
And this is not like a computational lower bound. This is
No, this
information theoretically.
Yeah,
this is
exactly.
not possible. Yeah. Oh, that's a very nice result. Okay.
Yeah. Actually, we talked about this recently, and I attended this talk after this. We discussed it. It's very recent. Yes. Yifeng.
It's a really nice talk. So I have a question. So you give a 6 approximation for this, like by a kind reducing to like Feldman and Hall stock 13, the first price versions, like the 2 approximations. So like so we know that for the fractional subadditive buyers, you're able to get 2 approximations. Like, is there any lower bound result, like ruling out, like whether 2 is not achievable? Like, what is
No. We don't have a better lower bound than 2. 2 is still the best, the largest lower bound we have. So it's possible that it ends up being 2 for subadditive. Yeah. All we have here is an upper bound of 6, but
I see.
the current best lower bound is 2.
So like another question is like, do you remember? Do you have an idea like for the stochastic paper, like for calculating the when you're approximately optimal allocation against offline optimal, what is the input look like the input of the subadditive function?
You mean the offline that's possible in polynomial time?
Yes.
So it's using demand queries.
Demand curves.
Yes, it's using demand queries, and it is basically so the LP relaxation can be solved in polynomial time using demand queries, because the demand queries are actually a separation oracle for that linear program. And then there is not so simple way of rounding this solution that requires it's a complicated coupling argument, but at the end it gives a 2 approximation with respect actually to the fractional solution. Yeah.
I see. Yep. Thanks.
Yeah.
Big question. Do you know if there's a way to explain the algorithm to someone who doesn't know like auctions?
To explain this algorithm?
Yeah. Maybe no fixed point there.
I mean, the thing is that the fixed point theorem guarantees the existence of these mappings. What's easy to explain is that once you have these mappings, the algorithm is this simple thing. Like you sample once each distribution, map them to bits.
Right.
I mean, bits is just a name
Right.
for number per item, right? And then set these as use them to set the thresholds, just the maximum. But yeah, I don't know how to do it without the fixed point. I mean, it's not even explicit, so there's not much intuition beyond. I mean, the best intuition we have is that it's like running an auction.
I see.
That's yeah.
okay.
But this at the end, it's like a black box that that gives this. Yeah. And it's not the only guarantee we have on this is that inequality, right? There's no. It's not like these bits approximate the value in just this inequality that holds. Yeah. And this can be interpreted as the utility in an auction. Yeah. Sorry, I don't have much more
Yeah.
intuition than that. Yeah. Yeah. Sorry. Yeah. Yeah.
So for 3-item auctions,
Okay.
that's the smallest number of items where subadditive differs from fractionally subadditive.
Yeah.
Have you thought about whether a lower bound better than 2 could be proved for that case?
No, actually, no. No. But it's a good question. Yeah.
I
No,
feel like it might be fruitful to just like do a computer search for instances where
it's true. It's
you
true.
know 3 items and 3 bidders or something, and
Yeah.
small enough
yeah.
search space that you might be able to just
Yeah.
make that example.
Yeah, it's true. Especially because I mean the two lower bound is just 1 item and 2 bidders.
Yes.
And 2 agents. Yeah. No, it's true. We haven't. It's a good idea. We haven't tried, but I don't know. I somehow have the idea that it's probably a 2 approximation the best possible. But yeah, I mean it's just because I imagine like everything is 2, so why wouldn't this be 2? But that's how it's a good idea to try that. Yeah. Yeah, Vasilis.
Hi, Andrés. Great talk.
thank you.
So I have a question regarding this open question that you had at the end with the posted prices. So here, when you say that do you think Kesselheim and Lucier paper gets the log m with posted prices, do you mean is it one price for each item for all bidders, or is it one price per item per bidder or something like that?
No, it's 1 price per item.
One price per item. Okay.
Yeah, fixed for the
I see.
entire realization, for the entire execution of the.
To get a constant, you just need to approximate. I mean, this is just to verify. Just this should be trivial, but like you just need to get now because of your result, you need to get a constant approximation with posted prices to the online optimal.
Yes. Right? Yeah. If you get that, then it will be a constant profit inequality.
Yeah. Okay.
Yeah.
Thank you.
Yeah. Great. No, thank you. All right. I think I guess. Yeah. Thank you. Thanks a lot for the questions. Yeah.